Diagnosing gearbox faults using vibration spectrum analysis, identifying mechanical issues through advanced vibration techniques. Introduction to gearbox condition monitoring, gear mesh frequency, GMF, and its importance, basic gear health assessment using the spectrum, effects of excessive tooth load on the spectrum, gear tooth wear and its spectral characteristics, backlash and gear eccentricity effects, gear misalignment and harmonic patterns, cracked or broken gear teeth, interpreting spectral patterns across fault types, conclusions and best practices. Gearboxes are critical assets in rotating machinery across industries such as power generation, oil and gas, manufacturing, and marine applications. Their reliability directly impacts system availability, safety, and maintenance costs. Gearbox condition monitoring aims to detect developing faults at an early stage so that corrective actions can be planned before catastrophic failure occurs. Among the available techniques, vibration analysis, particularly frequency spectrum analysis, remains one of the most widely applied and effective tools for gearbox diagnostics. From an engineering perspective, gearbox vibration signals are complex because they contain contributions from shafts, gears, bearings, and structural resonances. Unlike rolling element bearings, where specific fault frequencies are well defined, gear faults often manifest as changes in existing spectral components rather than the appearance of entirely new frequencies. Therefore, gearbox diagnosis relies heavily on trending, pattern recognition, and understanding how mechanical defects influence vibration modulation mechanisms. This presentation focuses on diagnosing gearbox faults through analysis of the vibration spectrum, with emphasis on the gear mesh frequency, GMF, its harmonics, and associated sidebands. These spectral features provide insight into gear health, load conditions, alignment, and tooth integrity. However, it is important to recognize that spectrum analysis alone may not uniquely identify every fault type. Best practice requires correlation with time waveform analysis, time synchronous averaging, TSA, where particle analysis, and, when possible, visual inspection. The material presented follows established condition monitoring principles used by vibration analysts and reliability engineers. The objective is to equip engineers with practical guidelines for interpreting spectral changes associated with common gearbox problems, understanding the physical forces behind those changes, and applying this knowledge in real-world machinery diagnostics. The gear mesh frequency, GMF, is the dominant frequency component in gearbox vibration analysis and forms the foundation for most diagnostic interpretations. GMF is defined as the product of the number of gear teeth and the rotational speed of the gear shaft. Physically, it represents the rate at which gear teeth come into contact and transmit load. In a healthy gearbox operating under steady load, GMF typically appears as a stable, narrowband peak in the vibration spectrum. Harmonics of GMF are integer multiples of the fundamental gear mesh frequency and arise due to nonlinearities in tooth contact, stiffness variations, and structural transmission paths. While the presence of some GMF harmonics is normal, changes in their relative amplitudes often indicate abnormal conditions such as wear, misalignment, or backlash. Engineers must therefore evaluate GMF not in isolation, but in the context of its harmonic structure. Another critical diagnostic feature associated with GMF is the presence of sidebands. Sidebands occur when the gear mesh vibration is amplitude or frequency modulated by another periodic process, most commonly shaft rotation. These sidebands appear symmetrically around GMF and its harmonics, spaced at the rotational frequency of the affected gear. The pattern, spacing, and amplitude of sidebands provide valuable clues about the nature and severity of gear defects. Understanding GMF behavior allows engineers to distinguish between normal operating conditions, load-related effects, and true mechanical faults. Accurate GMF identification also requires precise speed measurement and correct tooth count data, reinforcing the importance of high-quality measurement practices in gearbox analysis. A basic assessment of gear health using the vibration spectrum focuses on identifying changes relative to a known baseline. In a healthy gearbox, GMF amplitude remains relatively stable over time, harmonics are limited in number and magnitude, and sidebands are minimal or absent. Any deviation from this pattern warrants closer investigation, particularly when changes trend upward over successive measurements. An increase in GMF amplitude may be associated with increased load, changes in operating conditions, or developing mechanical issues. While higher load naturally increases vibration energy at GMF, unexplained amplitude growth under similar operating conditions can indicate tooth surface distress or alignment problems. Therefore, load context must always be considered when interpreting GMF amplitude changes. The appearance or growth of GMF harmonics often reflects increased nonlinearity in gear meshing. This can result from uneven tooth contact, stiffness variations due to wear, or backlash effects. Harmonics extending to higher orders suggest more severe or widespread contact irregularities. Additionally, the emergence of sidebands around GMF and its harmonics is one of the most important indicators of gear defects. Sidebands spaced at shaft speed indicate modulation caused by once per revolution variations such as eccentricity, wear, or cracked teeth. By systematically evaluating GMF amplitude, harmonic content, and sideband structure, engineers can form an initial assessment of gear condition. This assessment serves as a screening tool to prioritize further analysis using advanced techniques such as TSA or time waveform inspection. Tooth load has a direct and significant influence on gearbox vibration characteristics. As transmitted torque increases, the dynamic forces at the gear mesh also increase, resulting in higher vibration amplitudes at the gear mesh frequency and its harmonics. From a spectral perspective, a gearbox operating under high load will naturally exhibit elevated GMF levels even when no fault is present. Excessive tooth load becomes a concern when it exceeds the design limits of the gear set or when it is unevenly distributed across the tooth face. High localized stresses can accelerate surface fatigue, leading to pitting, scuffing, and wear. In the vibration spectrum, this may initially appear as a gradual increase in GMF amplitude without pronounced sidebands. Over time, as wear develops, modulation effects may introduce sidebands at the rotational frequency of the loaded gear. It is important for engineers to avoid misinterpreting high GMF amplitude as an immediate fault indication. Load-related effects must be correlated with process data such as torque, power, and operating mode. Trending GMF levels against load provides a more reliable assessment than absolute amplitude alone. When excessive load persists, secondary spectral features such as harmonics and sidebands typically become more prominent, signaling the transition from normal load response to actual mechanical degradation. Understanding this progression allows maintenance teams to intervene before irreversible damage occurs. Gear tooth wear is one of the most common gearbox faults and develops gradually over time due to friction, contamination, inadequate lubrication, or excessive load. As tooth surfaces wear, the stiffness of the gear mesh varies periodically as each worn tooth engages, introducing modulation into the vibration signal. In the frequency spectrum, tooth wear is typically characterized by the appearance and growth of sidebands around the gear mesh frequency and its harmonics. These sidebands are spaced at the rotational speed of the worn gear, indicating amplitude or frequency modulation caused by uneven tooth contact. As wear progresses, multiple sidebands may form, creating a distinct family of peaks around GMF. Another important effect of tooth wear is the excitation of gear natural frequencies. Impacts during meshing can excite resonances in the gear or gearbox structure, resulting in broader spectral peaks with sidebands. Additionally, higher-order GMF harmonics, such as the third gear mesh frequency, often increase in amplitude as wear severity increases. Engineers should monitor the trend and symmetry of sidebands, as well as changes in harmonic content, to assess wear progression. Early detection allows for lubrication improvements or load adjustments, while advanced wear may require planned gear replacement to prevent secondary damage. Backlash and gear eccentricity introduce periodic variations in gear tooth contact that significantly affect vibration spectra. Backlash refers to excessive clearance between meshing teeth, while eccentricity arises from off-center mounting or bent shafts. Both conditions cause the transmitted load to vary once per revolution of the affected gear. Spectrally, these faults are characterized by sidebands around the gear mesh frequency, spaced at the shaft rotational frequency. Unlike advanced wear, eccentricity often produces a limited number of sidebands, sometimes only a single dominant sideband on either side of GMF. Nonlinear contact behavior may also cause the first and third GMF harmonics to become dominant. In cases of backlash, an interesting diagnostic feature is that GMF amplitude and associated natural frequency peaks may decrease as load increases. This counterintuitive behavior occurs because increased load temporarily reduces clearance, improving contact stability. Recognizing this pattern helps differentiate backlash from other faults. Accurate diagnosis requires careful comparison of spectra at different load conditions and confirmation through time waveform analysis. Understanding these subtle spectral signatures enables engineers to identify mechanical looseness issues before they lead to accelerated wear or tooth damage. Gear misalignment occurs when gear shafts are not properly aligned, resulting in uneven tooth contact across the face width. This condition generates additional axial and radial forces during meshing, increasing vibration energy and accelerating wear. In the vibration spectrum, misaligned gears typically show high gear mesh frequency amplitudes accompanied by pronounced harmonics, particularly at twice the gear mesh frequency. The second GMF harmonic often becomes the dominant peak, distinguishing misalignment from other gear faults. Sidebands may also be present, but their spacing and symmetry can differ from those caused by simple wear or eccentricity. Misalignment can produce sidebands around multiple GMF harmonics. And these sidebands may be spaced at twice the shaft rotational frequency rather than once per revolution. This reflects the angular nature of misalignment and the resulting load distribution pattern. From an engineering standpoint, misalignment is especially critical because it affects not only gears but also bearings and seals. Early detection through spectral analysis allows for corrective alignment before widespread damage occurs, improving gearbox reliability and extending service life. Cracked or broken gear teeth represent severe faults that can rapidly lead to gearbox failure if not detected early. A cracked tooth introduces a localized stiffness reduction, while a broken tooth causes a complete loss of load-carrying capability at one point in the rotation. In the vibration spectrum, these faults generate a high-amplitude peak at the rotational frequency of the damaged gear. Additionally, sidebands appear around the gear mesh frequency, spaced at the gear's turning speed. Gear natural frequencies may also be excited due to impact loading as the damaged tooth engages. However, spectrum analysis alone may not always provide a clear indication of a cracked or broken tooth. Time waveform analysis is often more effective, revealing impulsive events occurring once per revolution. In a gear with multiple teeth, one pulse in the waveform will appear significantly different, corresponding to the damaged tooth. Engineers should treat these spectral and waveform indicators as urgent warnings. Immediate follow-up inspections and corrective actions are necessary to prevent secondary damage to mating gears and bearings. Effective gearbox diagnosis requires comparing spectral patterns across different fault mechanisms rather than focusing on isolated features. Tooth wear, misalignment, backlash, eccentricity, and cracked teeth all influence GMF, harmonics, and sidebands, but in distinct ways. For example, uniform increases in GMF amplitude often relate to load, while sidebands spaced at shaft speed point toward modulation-based faults. Dominant second GMF harmonics suggest misalignment, whereas strong once-per-revolution components raise concern for cracked teeth or eccentric gears. Trend analysis is particularly important. Gradual, consistent changes typically indicate wear-related issues, while sudden spectral changes may signal acute damage. Comparing data across operating conditions further improves diagnostic confidence. By systematically evaluating these patterns and understanding their physical origins, engineers can move from symptom recognition to root cause identification, enabling more accurate maintenance decisions. Diagnosing gearbox faults using vibration spectrum analysis is a powerful but nuanced process that requires engineering judgment and experience. GMF, its harmonics, and sidebands provide essential information about gear condition, load effects, and mechanical integrity. However, no single spectral feature should be interpreted in isolation. Best practice involves combining spectrum analysis with complementary techniques such as time waveform analysis, time synchronous averaging, and wear particle analysis. This integrated approach improves fault discrimination and reduces the risk of misdiagnosis. Accurate data acquisition, consistent measurement practices, and reliable baseline data are critical to successful gearbox monitoring. Engineers should also maintain close collaboration with operations teams to understand load and process influences. By applying these principles, maintenance and reliability professionals can detect gearbox faults earlier, plan interventions more effectively, and significantly reduce the risk of unplanned downtime and catastrophic failures.